All right, so welcome to your next physics lecture. We're going to continue talking about energy, except we are going to approach it from a little bit different standpoint. We're going to use a different kind of common physics example. We're going to look at springs today, which are a little more interesting than you might think. A couple of administrative issues first. As I'm recording this is 15 March of 23. We go on spring break next week. And I realized that we haven't done a test in a few weeks. And we're starting to get, starting to load up on information here. So I don't want you guys to have to stress about it over spring break. And I don't want to make the content of the exams too heavy. So what I'm going to do is I will put up an exam. Exam 2 is going to go live tomorrow morning. It's Thursday at about 8 o'clock in the morning, I think is what I have scheduled for. And you're going to have until Saturday at midnight to complete it. It's all going to be online again. It's 10 questions. The first 7 of them are going to be directly out of the homework, so you should have no problems with those. And the last 3 are going to be some things that I made that are going to require you to think a little bit more, and you're going to have to upload a couple of documents, just some sketches of free body diagrams and all. So expect them to be a bit more challenging, but it's nothing that you can't handle, especially given that you're going to have a couple of days to work on this. So as a result, I will not be lecturing on Friday because I'd rather you guys just work on the test and finishing up the homework, which is also due on Friday. And then we'll go away. We'll have spring break, and then we'll come back. And I think we have something on the order of 4 or 5 weeks left in the class after that, and then we'll be done. And you guys will all be expert physicists. Like I said, today we're going to continue our discussion about energy, but we're going to do something a little bit different. We're going to look at springs. So if I create some system here, so let's say that I have some mass here, some block of mass M, and it's attached to a spring. Let's take a few minutes and let's draw out some forces in a free body diagram here. Obviously, we know we have the weight force, which is just going to be our mg here. There has to be an equal and opposite force, so there's our normal force that we know, which is going to be the opposite of the weight force. Now, just remember, when I do this, as always, this negative just means that it's the opposite of the weight force. So pay attention to your signs. If you're using down, if you're using gravity as acting down, then your G is going to be negative, which is going to end up ultimately making the weight negative and the normal force positive. If you pick down as your positive direction, then up is going to be your negative direction. It's not a big deal. Just watch your signs on that. So we've got this normal force and this weight force, which we're very familiar with. We are also going to have in between this box and the ground, we're going to have some coefficient of friction. So remember mu, which means that whenever this thing moves, we're going to have to deal with a force due to friction. So let's say, for example, that we want to apply a force this way. So basically, we're going to pull this thing away from the wall, but it's attached to the spring. Now, because we're pulling this thing, we incur an opposite force of friction. So this is our mu sub n, or our mu n. But we've got another force now that we have to deal with. You've probably all played with a spring at some point in your life. Certainly, we've all used springs at some point in our life, whether it be in a clock or a watch or a car or something. We've all encountered springs. So we kind of know intrinsically how this is going to work, right? We're going to have to pull against this spring. Well, this spring is going to want to pull back. So it's going to exert some force. The spring always wants to restore itself to a position of rest. So there has to be a way to quantify the amount of force that is required to deform the spring. So we think about the things that are going to affect that force. The easiest thing to think about, what will control and affect that force. Let's get a marker here. Is going to be the distance that we stretch the spring. So this is some displacement, right? Delta X. The further we stretch the spring, the harder it's going to want to pull back. That seems consistent with how springs work. The other thing that is going to affect this force is going to have to do with the physical makeup of the spring. So things like how many turns are in the spring, what's it made of, how thick is it, how stiff is that spring? If you think about a slinky, right, just a toy, those things are pretty flexible. They're not very hard to deform. They're not very stiff. But if you think about the spring, say in the shocks on your car, that's a spring. But they're large, right? And it's very, very difficult to compress them, which is kind of the point, right? You want to absorb the force of the car that weighs some 2,000 pounds that bounces in a pothole or something. Well, you don't want a really loose spring there because then you just bounce up and down. So you don't want that to happen. So you want to make them rigid. So all of those things factor into a quantity that describes the kind of physical properties of the spring. And we're going to call that the spring constant. And usually we use K for this. So the spring constant kind of measures that. So the force, the spring force, is dependent on the spring constant K and the displacement. So that's our spring force, K delta X. But what we can do is we can say that this spring force represents an amount of work, right? So if the spring force represents an amount of work that we have to do, Because remember, there's a relationship between work and energy, work and force, right? Force is what we're applying to do some work. If we remember from last time that work looks like FD cos theta, where theta is the angle between our applied force and the direction of motion. So in this case, our theta is going to be 0 or 90, if you like to think about it that way. We're not pulling this thing up and down a hill or anything. So our cos theta term goes to 1. So the work in the spring system is FD. This looks real similar to FD, right? In fact, we can rearrange this. Delta X is a displacement. That is a distance, right? So this is the same thing as KD, if you like. So what we'd like to do is make something on the left-hand side here, or on the right-hand side, look like FD. We already have an F. So if we divide through by D, we get F over D is just K. So we don't really, that's not really what we want. So we have to take the inverse of D to make that work. So if we multiply this by 2D F over D equals K. Right, so look what happens. That should be a multiplied by another D. So you basically get a D squared, right? So what happens, one of those D's cancels. And we also need a D squared over here to take care of it. So we get something that looks like FD equals KD squared. Well, that's interesting. If this is work, right? Work is FD cos theta. So that's the work. So now we have this in terms of energy, right? We have in terms of joules. Well, if the spring is the only thing doing the work, then, well, let's first of all, let me do one more step here. Let's put it back in terms that we had. So D, remember, we did a substitution there. So let's put it back. So let's go F delta X equals K delta X squared. What does this look like? We have some energy here, and we have some energy here. But this is a delta X. But usually with energy, we don't typically deal with our displacement, right? Except for gravitational potential energy, we have the MGH, where H is our displacement. In order to save some time, and because it gets a little nasty, I'm not going to do the whole derivation for you, but you can look it up. Since this is the energy in the system, and that is the only energy that the spring is giving us, FD, that's also got to be the potential energy for the spring. That's all the spring potential there is. And if the system is closed, then if we take the negative of K delta X squared, that's got to be the kinetic energy. And if we do a little bit of mathematics, like I said, I'll leave it to you if you really care. You can do you can get a 1/2 out of this. And so what we get is the kinetic energy of the spring is a negative 1/2 kx squared. Looks a whole lot like our kinetic energy of just a gravitational system, right? 1/2 mv squared. Except now, here's the difference. In gravitational energy, with gravitational potential, the thing that the potential was dependent on, remember gravitational potential looks like this, right? It's dependent on the acceleration due to gravity, the mass of the object, and the height it is above whatever you've called zero. When we talk about gravitational potential, the thing that is causing the motion, right? In order for there to be motion, there has to be an acceleration, right? There has to be a force in order for there to be motion. If there's a force, there must be an acceleration because Newton's second law equals ma. So what we should work out here is that in gravitational potential energy, the thing causing the motion is the acceleration due to gravity. And it's the amount of gravitation that you're going to experience is certainly going to scale with the mass of the object and the height. But with a spring, we don't have that problem, right? We're going to assume in all these instances, by the way, that the spring is massless. The reason for that is because when you start trying to do spring constant calculations and account for the mass of the spring, then your K value gets very, very strange, and it's really difficult to work with mathematically. So for the scope of this course, we're going to assume massless springs. Now notice in my diagram here, I am accounting for gravity. Okay, gravitational acceleration is here, but it's only acting in the y direction. So it has absolutely nothing to do with this x direction movement. But we certainly have something that is going to impart energy into the system, which is the spring, in the x direction. But it ain't gravity. Got nothing to do with gravity. So it's a function of the spring. Thus, that energy has got to look like f d cos theta. That's the work required to extend the spring. We know it's a function of k, which is the spring constant, and the distance you displace that thing. So now what we've done really with the spring equations, all we've done is we've said, okay, this force has nothing to do with gravity. This force is all about the spring. And the only thing that we care about with the spring is how far we stretch it and kind of its physical makeup, its spring constant. So all we've done is converted things that think in terms of gravity, mgh, right, or gravitational potential, which is going to be a velocity, which looks like our roller coaster problem. Now we've converted that into things that are in terms of K and X. So here's our 1/2 kx squared. That's why this looks really, really similar to 1/2 mv squared. Another way to think of it is the two things that change kinetic energy in a gravitational system are certainly going to be the mass of the object and the velocity of the object. We need an equivalent in the spring. So the equivalence of the thing that is being moved in the spring, right? The mass equivalent is the spring constant, K. The thing that is the equivalent of the velocity is the distance here. That's our other dependent variable. So we get a kx squared. And again, like I said, the math details are not too important here, except that you get a 1/2 factor comes out of here. And so there's your spring kinetic energy. So what we can do now, since we have this system set up and we have all of the forces labeled, this turns into just another sum of the forces problem, right? There's nothing new here. The only thing we've done is we added the spring force. And we know that the spring force is just K delta X. Remembering your signs, whichever direction we chose is positive and negative. And now any problem I give you, if I ask you something like, how far do you have to stretch the spring in order for the box to slide backwards? Well, in order for it to slide backwards, we have got to overcome the frictional force, right? Or think of it another way. If you want to overcome frictional force and move the box that way, we need to find out how much force we need to apply. So F equals ma. And all we have to do now is first of all find out this frictional force. But now instead of just being frictional force acting in that direction, we've also got a spring force. The frictional force is based on the coefficient of friction and the normal force, which is in turn based on mass and gravity. So the frictional force is based on coefficient of friction, mass, and the acceleration due to gravity. So that is one source of energy in the system, gravitational energy. And the energy of the spring, that's creating some force. So we have our K delta X, which does not depend on mass and gravity, because that only affects the y direction motion. This affects the x direction. The only thing that's affecting the x direction there is the spring. So the only things in that force have to do with the spring. So this, again, like I said, becomes just a simple sum of the forces problem. This is just a simple sum of the forces problem. Just like we've already been doing for the last couple of weeks. I can ask you anything I want here, right? And you should be able to do it. What if, I'm not going to actually make you do this problem because I actually got a few cups of coffee this morning, so I don't feel like being excessively cool. But it would be a fair thing to ask you to be able to do given more time. I could certainly do something like this, right? Here's an inclined plane problem. We know how to do this. If we want to find, for example, the magnitude of the acceleration of the block up or down the hill, depending on how we're pushing or pulling or whatever, we could do that. The only thing I did here is I set up another inclined plane problem, except now I'm trying to pull the box up the hill, but I'm being opposed by the spring. This is a really great way to build things like exercise machines, right? If you have, imagine you have something that you want to train your lower body, right? And you want to train to pull things using your legs. Well, what you might do is put on some sort of harness, some kind of strap, and pull a weight behind you. Well, we need that to be adjustable. In other words, we want the resistive force to increase. So a way we can do that is by making a bigger and bigger rock for me to have to pull. Well, it's going to be difficult for a gym or whatever to supply and find a whole bunch of different kind of rocks or bricks or whatever to pull. And now the customer has to go and swap out chains and connections, and they could break and that kind of thing. So an easier way to do this, as far as a machine, is we have a block of known mass. We attach it to a spring, but we change the tension in the spring, effectively changing the spring constant. So you might have a knob or something that you would turn that will increase the spring tension, thus making it harder to pull this, right? You change the delta X or you change the K. So it makes that exert more force. So now it effectively makes this block from a 10-pound block to a 100-pound block if you want, depending on your spring. And now, if I use this as gym equipment, I'm just pulling the same block. I don't have to change anything except the way the spring behaves. And if I want to give an added challenge, I can increase this. You've probably all seen treadmills that have the hydraulics on the incline. That's all you're doing, right? Now we remember from our work example, our energy example yesterday, we were talking about an exchange of energy. And we're talking about how work is energy. And if we think about it in terms of like exercise and things, you'll hear about burning calories. Well, that's doing work. Remember the example that I gave of my car runs out of gas and I'm going to push my car to the gas station. Well, the amount of work, the amount of calories I'm going to have to burn in doing that is going to be dependent on the force that I have to apply to move the car and the distance I move the car. So all I did there was I looked at the energy exchange between me and the force of friction. In this case, we're just adding another spring. An example that I like to do sometimes with the energy thing is I give you the car problem, and then I'll say, all right, which is it going to be easier to do? Push the car 1 mile to the gas station, or take an empty gas can, walk 1 mile, fill the gas can up with gas, and then walk back. So a couple of things in that. Your distance obviously is going to double. So the amount of work required is going to change because of the distance. The mass is going to change, right? Because now instead of pushing a 2,000-pound car, I'm carrying a 2-pound gas can, but then I'm going to put gas in it. And depending on the size of the gas can, you're going to increase its weight, right, by adding more gas. And so now I have a bigger mass, but I have to walk back and expend calories the other way. So a good question might be, which one is easier to do, right? Which one are you going to do less work doing? Because as I said, I'm a physicist, I'm lazy. So I want to do the least work possible. Another way you could approach that question would be find the point at which the distance, when does the distance become so large that it is more efficient work-wise to just push the car as opposed to walking and getting gas and walking back. So lots of different things you can do. Now, having said this, I have mentioned a couple of times a term that has to do with energy and forces that we haven't really given a whole lot of thought and definition to. And that is the difference between conservative and non-conservative forces. So we need to define what those are. This has nothing to do with politics. So before you get pissed off and you start sending me emails about vote for Bernie Sanders or Donald Trump or whoever's winning the popularity contest at this point, that's not what I'm talking about when I say conservative and non-conservative forces. I'm talking about something different. I'm talking about from a physics perspective. A conservative force is path independent. What this means is the amount of energy required to go from one point to the other does not depend on the path you took to get there. I'll show you an example. Let's say that we have, let's do the roller coaster problem again. Really boring roller coaster. There's people inside the roller coaster. They're sad because this roller coaster sucks. They travel along this path. It's a straight course, it's flat, constant velocity. Like I said, roller coaster really sucks, not a whole lot of fun. You can calculate the amount of energy that is required to move this roller coaster car from here to here. Very easy, right? That's just an energy calculation. So we know that that's just work. The amount of work that we need to do in order to move that car from point A, point B, or over delta X. We're on a flat track, so cos theta goes to 1. So work is just the amount of force that we apply over the whole distance. That's the amount of work we did. Now let's make the roller coaster a little more interesting. Let's do this. Here's no roller coaster. Now the people are going to be happy because roller coaster is a little more fun. Let's assume the roller coaster starts and stops at the same elevation above the ground. Call that our height. Let's think about this in terms of energy and the amount of work that was done. Well, the energy, remember, in this case is going to change between kinetic and potential. Well, it does here too, right? Because at some point, this thing's going to go faster and then it's going to go slower, whatever it's going to do, right? There's some amount of energy expended. Let's just think in very generic terms without doing any math, without doing any equations. We have some amount of energy in the system, right? Some total amount of energy in the system. That's all we're ever going to have. In this case, we've got some total amount of energy in the system. When we get to the end, we better have the same amount of energy. We haven't lost anything. Now I'm going to get to that in a bit. So here, we've got some total amount of energy. So where did the energy come from here? Well, here, maybe it came from an applied force. Maybe I pushed this. But still, I did something to impart energy. Here, the energy is probably just coming from gravity. So I'm just let gravity carry this car, but it imparted some energy. And the total amount of energy that's in this thing is only a function of gravity and height. So as the car travels down the hill, we're trading potential for kinetic till we get to the bottom. It's all kinetic energy. But at the bottom of the hill, remember, kinetic energy is equal to the total potential that it started with, because all the energy has been converted into kinetic. We go through this loop. So we get to the top of the loop. Notice the top of the loop is lower than where we started. So we still have some energy left, even though we're losing some. And we're coming up around here. And then we drop off again, and we gain energy. But then ultimately, we have to come back up the hill. So we're going to trade kinetic for potential until we get to the top of the hill. And then we're back to all potential energy. But if we haven't lost anything, then the amount of energy that we had at the beginning is the same as the amount of energy we got out. So this work here, this potential kinetic energy, this is a conservative force because it is path independent. The amount of energy in the system did not depend on how we got from point A to point B. Right? We're going to assume that this whole point A to point B is the same delta X here. So we didn't change that. So no matter what path we take to get back to where we are, as long as we end up at the same place relative to where we measured our energy, if that didn't change, it's conservative force. What about a non-conservative force, though? Non-conservative forces, if conservative forces are path independent, then non-conservative must be path dependent, right? In other words, the longer that you do this, right, the longer path you take, the more energy is going to be required. Non-conservative forces in physics generally are things that remove energy from the system. So an example of a non-conservative force is friction. Remember, when we do frictional force, that's just mu n. Well, we can always account for this, right? We can just do our free body diagram problems and we can find this. But what happens? The longer we're on this track, the more energy we're going to lose from friction. All of these, remember, we were doing with no friction, right? We're doing frictionless track. But what if we do add friction? What's going to happen? If we account for the friction between the roller coaster car and the track, if we build this thing such that we start at this top of this hill at H and we let it go and we just rely on gravity, we're never going to get back here because we're losing energy on these loops and these hills because we're rubbing against the track. Now here, we're going to lose energy, right? We know that this thing is going to slow down because it's losing energy due to friction. We're going to get to the end. But as soon, even if the coefficient of friction is the same, as soon as we change the path, we lose more energy. Because friction is a non-conservative force. It is path dependent. So when we talk about conservative and non-conservative forces, that's what we mean. Things that you can arbitrarily say are up, down, left, right, doesn't matter. And it doesn't matter how you got there. Non-conservative forces, we're going to have to be a little more careful with direction. Notice when we did these energy problems, work and things like that, we weren't too concerned about direction, right? We can say that the total energy is just the sum of the kinetic and the potential, whatever those happen to be. But when we started doing two-dimensional problems and we started worrying about friction, now I have to be really careful about what direction the friction is in, because it's a non-conservative force. Everything we've done up to this point, when we've done friction, has been planar. In other words, just doing this and adding friction, or making an incline and doing friction. When you start accounting for friction here, it gets a little more nasty. So we're not going to do that. Because that now you're going to have to worry about, well, okay, as this thing goes up the loop, let's say, at some point gravity becomes less of a problem. The normal force becomes less of a problem, right? At the top of the loop, for example, gravity is acting down, but the normal force, there's not really a force here pushing the car back. Well, I mean, there's the normal force of the track pushing on the car, but like centrifugal force, for example, there ain't nothing acting that way. It's pulling the car down. So because of all that, that frictional force is going to change. It's going to be time dependent. Anything you have something that's time dependent, we're going to need calculus to do. These are path dependent and independent. So no calculus involved. But if something that's time dependent, you absolutely need calculus. And that's when you'll see us write something like df/dt, the derivative of force with respect to time, is going to give you something that's time dependent, and it gets really nasty. For example, let me show you one little thing here. Again, not required to know this. So our position x, right? If we take the derivative of x, dx dt, that's our change in position with respect to time, that's our velocity. And if we take change in velocity with respect to time, that's something called acceleration. Now, everything we've done in this class and everything we will do in this class, acceleration is going to be a constant. And if you know anything about calculus, we know that the derivative of a constant is 0. but sometimes it's not. So there is a quantity where acceleration is not constant, that you can take the change in acceleration with respect to time. This is not a self-description. This is actually what it's called. It's called jerk. So a lot of times you'll hear engineers and rocket scientists talk about jerk in a system. That has to do with how quickly the acceleration is changing. So if we deal with things like non-conservative forces, then we typically have to deal with things like jerk, which again requires some calculus to do with some derivatives. So again, we're not going there this semester. We're in this course. So I think that's where I'm going to stop with the energy discussion. Remember, the test will go live tomorrow morning about 8. And you'll have until Saturday at midnight to complete it. And then go do whatever it is you do on spring break. Don't think about this class. Don't think about physics. Just go have a good break and chill out and enjoy yourself. And then when we come back, we'll review quickly what we've done about energy and everything that you forgot and all the things that died along with the brain cells over spring break. And then we'll continue on with the course. We'll finish up energy and we'll start talking about collisions. We'll start talking about things hitting other things, which is a little more interesting. Okay. Aside from that, standard procedure. If you have questions, reach out to me. Even over spring break, I will be checking my email periodically. Can't guarantee I'm gonna get back to you within 24 hours over spring break, but I am going to be checking my email periodically. So if you have questions, email me and ask. And always, if you need more help than that, set up an appointment with me and come talk to me in my office. Other than that, I'll see you guys after the break.